Hi there, students. It's Mrs. Brunk again. Welcome back to Algebra 2, and welcome back to solving quadratic equations. And we mentioned in the last lesson, which was the lesson where we learned about how we could use graphing as a way of solving a quadratic equation. We learned that the solutions are on a graph where the graph crosses the x-axis. And we talked about how we were going to learn multiple ways to solve quadratics. And that's because some lend themselves to one method and some to others. And the method we're going to learn today is actually pretty limited, but it's still a very good way to solve quadratics. And it's going to be the method of factoring. But the limits on factoring is that not every quadratic equation is factorable. So if it is a factorable quadratic, then this is a great method to solve. And if not, then we'll have other tools that we can use to solve. So we basically follow four main steps when we solve by factoring. And remember, we just finished up a unit on factoring. And so, we're going to kind of put those skills to use today. And the four steps start like this. First of all, number one, move all terms to one side, and then set the equation equal to 0. So that to me seems like two steps, but so move all terms to one side and set the equation equal to 0. So in other words, we want to leave nothing on one side, and so in other words 0, and get everything on the other side. Now remember, we called solutions zeros. So this gives just another layer of meaning of when we say a 0 of the function. We want to know the values of x when the function equals 0. Step 2 is to factor. So to factor the quadratic. Number 3, set each factor equal to 0 and solve for each x value. And then 4, finally, write your answer as a solution set. And you can do them just like this. Sometimes I'll just say x equals and then x equals, or maybe I'll even write them as ordered pair. So this is not, necessarily the way that we always have to do that. So I'm going to kind of cross that out. It is a way you could do it, but it's typically, it's not done in that sort of ordered pair form. So, unless you were actually writing the coordinates as an ordered pair, like we did in the last lesson for the x-intercepts. Like we'd say if it crosses at -3, we'd say that coordinate was -3, 0. So that would be the solution. So step 1, move all terms to one side. Well, in number 1, that's already been done for us. So we have x squared plus 9x equals 0. So we know lots of different ways to factor, right? But our number 1 step is always to see if we have a GCF. Now typically, quadratics that have 3 terms won't have a greatest common factor other than maybe like a coefficient, of a numeric GCF. And that's because we'll have one term with an x squared, we have one term with an x, and then one that doesn't have an x at all, right? So, but in this case, because we don't have a constant term, or in standard form we don't have a c, we have x squared plus 9x, which means they both have in common an x. So our way of factoring it would just be taking out the x, and that would leave us with an x plus 9. And then, of course, on the other side, we have equals 0. So now we're on to step 3, which is now to take each of these factors and set them equal to 0. So if I set the first factor equal to 0, well, then I already know one of my solutions is, in fact, 0. We talked about that in the last lesson. Anytime there's not a constant term or a c, that means that the graph crosses at the origin, meaning that's one of the solutions. And then if I set x plus 9 equal to 0, to solve I'd have to subtract 9, which would give me x equals 9. And so there are my two solutions. They are x equals 0 and x equals -9. And if we were to graph this, maybe even just to confirm on a graphing calculator, we would see that in fact the ordered pair that would be on the graph would be 0, 0, and -9, 0. So sometimes you'll see the solutions written like that, probably more often than the way that they showed up here that we just crossed off. We'll see them either written as x equals, or we'll see them written as the ordered pair that is an x-intercept point. Okay, so I'm going to leave a couple of these. We're going to kind of jump around, and we'll leave a few of these for like some you try questions. So I think we're going to go on to number 4. So looking at number 4, 9x squared minus 25 equals 0. Well, you may recognize this is one of our special factoring patterns. This is a difference of two squares, or difference of squares pattern. 9x squared is a perfect square, 25 is a perfect square, and it's a subtraction. So remember those, when we factor those, we get two nearly identical factors. Just one of them is a plus and one of them is a minus, and the factors come from square rooting the two perfect squares. So we'd have one factor that's 3x plus 5 and one that's 3x minus 5. So then if we set each of these factors equal to 0, okay, setting 3x plus 5 equal to 0, in order to find out what x is, I would have to subtract 5, which would give me 3x equals negative 5, and then divide by 3, which would then leave me with x equals negative 5/3, or negative 1 2/3. And doing the same thing with the other factor, 3x minus 5 equals 0. We'd add 5 instead to both sides and divide by 3 now, which would give us x equals 5/3. Now you may remember in the last lesson we talked about that. We said if you don't have a middle term, a b term in other words, that actually means that the graph will always be symmetric about the y-axis, so that your zeros will always be opposites of each other, or your solutions will always be opposites of each other, and we confirm that here with that. So another way to write that is, again, is the ordered pairs of 5/3 comma 0 and negative 5/3 comma 0. And this is actually a really good example of why graphing is not a legitimate method to solve quadratics. Is, this graph certainly does not cross at integer values, and if you were going to try to estimate from the graph that, what are the chances you're going to estimate as negative 1 2/3, right? So, this is just kind of a ringing endorsement for algebraic methods to solve. So that actually leaves us with 2 and 3 here that I want you to pause the video and give both of these a try. Factor and set your factors equal to 0 to find your solution. So pause the video now and give 2 and 3 a try. All right, so thanks for giving those a try. So number 2, your solutions are 0 and 2, or 0, 0, and 2, 0, written as ordered pairs. And then for number 3, the solutions again are opposites of each other, because you see that one's one that doesn't have a b term, so symmetric about the y-axis. So x equals 2 and x equals negative 2, or 2, 0, negative 2, 0. Okay, so now let's take a look about if we have a trinomial. So those other ones just had 2 terms, these now have 3 terms, so we'll do a little more traditional factoring, binomial factoring. So with something like number 5, when we start off with just x squared, we're going to use our guess and check method, right? So we know that both of the binomial factors, if this is factorable, and at some point we're going to come across some that are not. Most of these should be factorable. So we know these are both going to start off with an x in our binomials. And then I'm looking for 2 factors that multiply to give me 21 and add to give me negative 10. And so right away I start thinking about like 7 and 3. And so actually negative 7 and negative 3 would work, because they would multiply to give me positive 21. And adding negative 3 and negative 7 would give me negative 10. So my solutions are going to be what makes this equal to 0, which at some point you're going to get to the point where you'll be able to just look at these and tell, and hopefully you're there now, that x equals 7 would be the value of x that would make that 0. And we're using the zero product property, which basically says that because I have a product of 2 binomials and the product of these 2 binomials is 0, that means either one of the binomials must equal 0 or the other, or both. Okay. And to make this one 0, x would have to be 7, and in this one, x would have to be 3. So again, you can write them as x equals, or you can use the ordered pair notation, which is 7, 0, and 3, 0. Number 4, okay, or I'm sorry, number 6. So number 6 you see that this one starts off with 2x squared. So you might be thinking, okay, I've got to use the AC method. But we always got to think about the, is there a GCF? And yes, there is a GCF here. But instead of, because our goal here is not to just necessarily factor, but to solve, instead of actually just factoring out a 2 out of the terms, instead we could just take everything and divide by, in this case, the GCF, which is 2. And since we have an equation here, we can even go over here on the other side and divide by 2 so that, we're following the division property of equality, right? And if we do divide that 0 by 2, it's still 0. So in effect, that just, reduces the entire equation by a factor of 2. Okay? And so now it turns out to be x squared minus x minus 12 equals 0. And when we factor, these are both going to start with x. And I know, let's see, factors that are going to multiply to negative 12, add to negative 1 would be negative 4 and positive 3, giving me solutions of x equals 4 and x equals negative 3. And again, you could write these as ordered pair as well. So maybe you'd say 4, 0 and negative 3, 0, or you could just say x equals 4 and x equals negative 3. So that worked out really nice that we could just divide that 2 out. But unfortunately in number 7, not all of those terms are divisible by 3. So we're kind of in that position where we have to use our AC method to factor. So again, our first step really is to get everything on the same side. These are all set up that way already. So if there were things on the other side instead of 0, we'd have to make sure everything got brought on the same side and 0 on the other. So unlike linear equations, where we try to get variables on one side and real numbers on the other, can't really do that in quadratics because we don't just have x terms, per se, like we'd have x squared and x terms. So there's no way to just isolate the single variable, at least not in these situations. So I'm going to go ahead and use the AC method. So let's see, A, which is 3, and C, which is negative 30. They make negative 90. So now I'm looking for factors of negative 90. That are going to multiply to negative 90, they're going to add to negative 13. Well, first thing that comes to my mind, a negative 15 and 4. But that actually makes 11. So I always think, those are not 4. Sorry. That's not right. 6. So that is not a pair that's going to work because if one was negative and one was positive, that would make negative 9. If the other was, then it would be positive 9, right? So then I start thinking, okay, so what about 30 and 3? Well, that's not going to work. What about 9 and 10? Oh, can't do that. What about 18 and 5? Oh, bingo, there it is. That's a very, that's not a very common factor of 90. But sometimes you got to play around with it for a while. So negative 18 and positive 5, they multiply to give us negative 90, and at the same time, they add to give us negative 13, excuse me. So that's our pair. So we're going to take our middle term, we're going to split it into a negative 18x and a positive 5x. Doesn't really matter which one we put first, as we recall. So there we go. So now we're going to split down the middle and factor by grouping. Out of the first pair, I could take a 3 and an x, leaving me with x minus 6. Out of the second pair, I can take a positive 5, leaving me with x minus 6. So there's that common binomial. So one factor is 3x plus 5, or those GCFs, and the other is the common binomial of x minus 6. So one solution is really easy to see. It's going to be the one that makes this one 0, so that means x is 6. Now the other one, eventually you'll kind of figure out the shortcut, but if we set the 3x plus 5 equal to 0, we'd have to subtract 5 and then divide by 3, giving us x equals negative 5/3. Well, the shortcut is you just look at the constant term here and you take the opposite of it and then divide by the coefficient. So when you feel comfortable doing that, then there's really no need to write that little equation, 3x plus 5 equals 0. So But, you know, as long as you need to, that's fine. Just saves you a little time down the road. So our two solutions are negative 5/3. Let's see. Oh, that's not showing up. Same color background. So we've got negative 5/3 and x equals 6. Well, here's a good time for a you try question. So go ahead and pause the video and let's make number 8 a you try question using the AC method. So pause the video now. All right, so thanks for giving that one a try. And the solutions to number 8 are x is equal to 1/2, or written as an ordered pair as 1/2 comma 0, and x equals negative 4/3, or negative 4/3 comma 0. Okay, so each of the examples we've done thus far has bypassed that first step, which was to get everything on one side and 0 on the other. So we haven't had to do that yet. So this next segment of the notes are going to involve us having to do just that. And so typically, I mean, it's like, especially like in number 9, where you've got just one term on either side, I mean, I guess technically you could move either the 2x squared to the right, or you could move the 5x to the left. Now, I typically will always move so that the leading coefficient, so in other words, the coefficient on the x squared term, is going to be positive. If I can avoid that a being negative, then I do that. So in this case, I would move the 5x over by subtracting it, and then we're left with 0 over here. Okay. So now this is one of those that we can just do the GCF factoring because there's not a C term. So we know that one of the solutions is going to be 0, and that's because in this case our GCF is to take an x out. So if we divide an x out, that leaves us with 2x minus 5. And then our solutions will come from setting this equal to 0, which makes x equal to 0. And this one, which is x equals 5/2. So again, if we set 2x minus 5 equal to 0, we'd have to add 5 and then divide by 2. And that's where the 5/2 comes from. Or alternatively, writing these in ordered pair form. So if they ask for ordered pairs, it would be 0, 0, and 5/2, 0. Okay, so it just depends whether they ask for them in ordered pairs, or if they don't specify, I guess it's your choice. So number 10, we've got this x squared all by itself on the right-hand side. So if we bring it over, we'd have to subtract it. And that would leave us with 6x squared plus 8x equals 0. And again, a really easy way to solve, just taking out our GCF, which is 2x. And that leaves us with 3x plus 4. If I set 2x equal to 0, I know that x is going to be 0, because I have to just divide 0 by 2, and of course that's still 0. And with this next one, if I set that equal to 0, I'd have to subtract 4 and divide by 3, so that's negative 4/3. So there's my two solutions. And again, number 11, you have choices. I mean, you've got two terms on one side, you've got two terms on the other. So just as a rule, I always try to move it so that the x squared term is positive. So I would choose to move the x squared minus 1 over to the left. So I'm going to subtract x squared, and at the same time I'm going to add 1. So that means all of this is gone on the right-hand side and just 0 left. On the left-hand side, 2x squared minus x squared is just x squared. And negative 50 plus 1 is negative 49. Now I know that that's a difference of squares because both are perfect squares, so I could factor. And I'd get x minus 7 and x plus 7, meaning my two solutions are x is 7 and x is negative 7. Now another alternative to that is we could have, once we got to this point, I'm just going to erase these and show you. So once I got here, or let's say this was the original problem, was x squared minus 49 equals 0. We talked about before how we get everything on the same side because we can't isolate the variable. Well, in this type of equation where we don't have a b term or an x term, we can isolate the x term. So we could just add 49 to both sides, and that would leave us with x squared equals 49. Now the only concern with using this method is that sometimes people forget that when they take the square root, which is what we do next, they forget that we get both a positive and a negative version for every positive number that we square root. We'll get, in this case, positive 7, negative 7. So as long as you don't forget to do that, this is another method. This is called taking the square roots, and we'll explore that more as we go along. And in fact, that might be the method that I will use on number 12, because rather than have to move that that 3x squared over to the right, which would then make it negative, or having to bring both the x squared and the 81 over to the left, I could instead just add x squared to both sides, leaving me with 4x squared equals 81, right? And then if I wanted to use the square root method, I could just simply divide by 4. Okay, remember when you solve, you go in reverse order of operations. So I first, and I always call that SAD map. Okay, you know, order of operations is PEMDAS, right? So reverse order of operations, which is how we solve, is SAD map. So we first undid any adding or subtracting by adding the x squared. And then we undid any division or multiplication by dividing by the 4, right? And then now that this is gone, the 4 is gone, we have that x squared. So now, to get x alone, we take the square root. Well, on this right-hand side, if I square root 81, I get 9. And if I square root 4, I get 2. And of course, there's always a positive and a negative version. So that would leave me with my two solutions of plus or minus 9/2. Now remember in the last lesson, we learned that a parabola could cross the x-axis 2 times, which a lot of them that we see cross twice. It might cross 1 time, just be sitting right there on the x-axis, right with its vertex there, or it might not cross at all. So typically we'll see 2 solutions, but there are situations where we have 1, or maybe we have no real solutions, and we'll have to look at what do we do when there's no real solutions. Now I'm going to select a couple more of these to do with you, and we'll leave the rest as part of your homework, along with the accompanying homework worksheet that goes along with this. So we'll have you complete that homework worksheet and the rest of these notes once we get done with a few more of these. So again, these are getting more complicated because there's terms on both sides. And I just would always plan on, if you are going to bring everything to one side, which you will always do unless you just have an x squared term and no x term, then I would always try to, if possible, make it so that your leading coefficient, your coefficient on the x squared, in other words the a, remains positive when you do that. So you choose the side to move it so that that's always positive. So taking a look at these problems, I think I'm going to choose to do number 16. So with number 16, I'm going to have to bring this negative 3x over to the other side by adding 3x. So I'm going to add the 3x to the 41x, and then I'm going to subtract 2, right? So I'll be subtracting 2 from 98, which then makes my quadratic be 4x squared plus 44x plus 96 equals 0. And if I'm not mistaken, I think every one of those terms is divisible by 4. So right away, I mean, I could divide that 4 out, factor it out and then divide it off, or just go through every term and just make sure everything gets divided by 4. Then we're using division property of equality. So that would leave me with x squared plus 11x, and if I divide 96 by 4, that means I get 24, and then that equals 0. And now all I have to do is find factors, it looks like I didn't leave myself a lot of space, that are going to multiply to give me 24 and add to give me 11. So that would be 8 and 3, both positive. If I set them both equal to 0, I'd have two solutions. One is x equals negative 8, and then x equals negative 3. Or again, ordered pair version would be negative 8, 0, and negative 3, 0. So there's my two solutions there. So sometimes it looks like it's going to be messy, but by the time you get everything on the same side and maybe divide off a greatest common factor, turns out to be not too bad. So like in that case. So all right, let's pick one more to do together. So it looks like number 17 is going to be one that we'll for sure have to use the AC method on. Well, maybe, I mean, you could do guess and check, but this one's one that we typically would do because it's going to start off with a coefficient other than 1. So again, I have choices here. I can move the 2x squared to the right, but then that's going to make that a negative leading coefficient. So instead, I'm going to bring the x and the 21 to the other side with the 2x squared, which would make 2x squared minus x minus 21. So we think about factors of the product of 2 and negative 21, so that's negative 42. And we need factors that add up to negative 1. Okay, well the first factors that come to my mind with 42 are 7 and 6, and that actually works perfect as long as the 7 is negative. So I'm going to rewrite that middle term, so 2x squared, doesn't matter which comes next, but I'm going to put the plus 6x, and then the minus 7x, then minus 21. We factor by grouping, and out of the first pair I can take a 2 and an x, leaving me with x plus 3, and out of the second pair a minus 7, leaving me again with x plus 3, and finally I just have to get my factored form, which does not leave me a lot of space here, and that would be 2x minus 7 and x plus 3. And if I set those equal to 0, and I'll just write my answers up here. I have x equals negative 3 and x equals positive 7/2. That's the one that would go to this one right there, right? So there are my two solutions, negative 3 and 7/2. So the remaining 4 questions on this page and the accompanying homework pages should give you plenty of practice for solving quadratics by factoring. And also apologize for all this snoring going on. You know, you're probably used to this by now. My little teaching buddy here, sometimes I have 2 and they're really loud. Just have 1 tonight. So hopefully she hasn't made you too tired with all her snoring, but she definitely has made me tired, so I'm glad it's time for bed. But that does it for today's lesson, and I will see you in class. Ooh, and then don't forget to finish. Sorry, I should have written these. We're going to finish these for homework. Oops. Finish for homework along with your worksheet.